Perfect. So until now, we looked at the Fn by Fs condition for characterization of our sample and hold. So basically, we had a condition where Fn by Fs was m by n, where m is an integer and n is taken to be 2 to the power p, and p is an integer. And this is basically called as a record length, and it is always taken as 2 to the power p. It makes us easier to calculate the fast Fourier transform. So that's the reason behind taking this n as 2 to the power p. So if we find the discrete Fourier series corresponding to length n, then we get n coefficients of discrete series, and if this relationship of Fn by Fs is valid, then we get to see only one coefficient being non-zero in the first half, means before n by 2, and the other coefficient being non-zero, which is just a mirror image. So it will be simply like all other bins are near about zero, and only two bins are showing the peak when this condition is satisfied. So by let's take a consider that by some unknown reason, if we are not able to sync Fn and Fs. So what can we do to fix the issue we will face regarding FFT leakage? So we talked about FFT leakage, and it occurs when Fn and Fs are not synced together to maintain their ratio. So when we look at the phenomena in time domain analysis. So we looked at the phenomena of FFT leakage in frequency domain. So we'll look at the same thing in the time domain. So when we concentrate on this sine wave, so basically if the input tone do not lie on the frequency bin, so what does it actually means? So we are basically, if the input tone is not lying on the frequency bin, then we are finding the discrete Fourier series corresponding to a sequence which is shown basically in the black curve, and where the ends of this sequence there is discontinuity over here. So this is the time domain analysis of what we are trying to analyze when we talk about fast Fourier leakage due to the unsynchronization of Fn by Fs to maintain this ratio. So the discontinuity in the end of n samples simply means that there is an impulse at the ends. So we find these impulse when the actual sign, the actual input signal should be like this, drawn from the green curve. But if there is a mismatch or not synchronized, then the black curve shows us the impulse. So there is a jump at the impulse, and how frequently the jump occurs is the question. So basically, after every n samples, where this n corresponds to the record length when we talk about the record length. So after every n samples, let's say as of now, after every n samples, this jump occurs, and this unsynchronized phenomena is non-periodic. This means the fundamental frequency of this jump is 1 by n samples, and it will have a whole bunch of harmonics, and this jump is basically causing the leakage when we take a rectangular window. So until now we were taking a rectangular window of m samples. So let's say we took a rectangular window of this. So we were considering all the samples, and this basically is a discretized signal. Just for the sake of simplicity, I have mentioned, like I have drawn it as a continuous signal, but this is basically look at it as if there are so many samples together that it is looking as a continuous signal, but this is actually a discrete signal. I have just drawn it continuous for the sake of simplicity. So hence after n samples, so our our samples are n, let's say we take a period of n. So after n samples, we have a jump again, and the jump consists of impulses which has got a lot of high frequency content, and that will simply like those high frequency content is basically the jump itself, the fundamental frequency of its and its harmonics, and those will add to the spectrum of the sinusoid, and that will result in the distortion, or let's say that will result in all the bins being occupied instead of just two bins. So if we analyze the same thing in time domain, so we have, let's say, n bins from 0 to n minus 1, and between those n bins we have a non-periodic signal which is not being synced with which is not being synced, or let's say which is not satisfying this condition. So that's why FFT occurs, right? So let's take a FFT leakage phenomena where we have n bins, and we have a signal which is not periodic, and we have fixed window length, and let's say the window is length is n bins. So let's draw all the sequences, as I mentioned earlier also. Let's draw all the sequences or the samples as a continuous wave for simplicity. So basically these are discrete samples clubbed together. I am just drawing a continuous wave for the simplicity. So when we take n samples from 0 to n minus 1 of this non-periodic sequence, and let's say we are just interested in some n samples. We are not interested from minus infinity to infinity of non-periodicity. We are just interested in n samples. So when we take n samples of this non-periodic sequence and make a periodic extension with a period of n. So every after we take we take n samples and repeat them itself after a period which is n, and then there is a discontinuity. When we plot that, then there is a discontinuity at the ends in the form of impulses or the kinks. So this is n, again it will repeat itself, again this is n, again it will repeat itself. So we take n samples and make a periodic extension. That is what we do for in order to obtain discrete Fourier series. So then we have kinks at every n samples. So this means that we have impulses at every n samples. So something we should note over here is that the unwanted part or the impulse is if we take a sample of n samples. So the data in between is fine. We are okay with that data. But in the ends, in the end parts, we are getting the impulses due to the non-periodicity or unsynchronization. So the kinks are only at the ends of this whole period. So again, let's take the same period of length, which is equals to record length n. So the data, so if we see this box, so the data in between seems quite okay. The data at the ends is problematic, which has the impulses or the kinks. So when we are using a rectangular window, so initially we were using a rectangular window like this, where all the samples were equally important. And we took it as m samples, and then we derived all the equation for the same, and looked at the FFT phenomena. So that was for rectangular window. But now we know in reality that the leakage is occurring due to this discontinuities in the end itself, not throughout the data. So most of the data is fine, just the ends are problematic and are contributing a lot to this FFT leakage phenomena. So then instead of taking a rectangular window, since we want the data, or we want the center window to be like this is the window of our interest, and we do not want the end parts. So basically over here, we do not want the end parts. So we introduce a function which waits for the important data and tapers off the waiting function in the end. So then we have our main period, we have our n samples, and we say that we take a function which tapers in the end and which waits for our data to be interested. So then when we multiply these two, so we will get some kind of a curve which resembles like this, where this is the product of these two functions. Hence, basically we multiply our sequence. So this is our sequence, uh, and we multiply with another sequence which remains constant for all the middle samples and tapers off smoothly at the ends. Thus, uh, the window, like what we actually do is we window the sequence before taking its Fourier coefficient. So initially, what we like earlier we did, we take a rectangular, we took all the samples, and then we took the Fourier series. But now, before taking the Fourier series, we window the signal. So this is how we window the signal. So intuitively, we can expect less leakage with respect to the case where we were taking large rectangular window. So let's take a look at some famous spectral windows, and let's say, so basically this is what we want. We have to wait for the data which is interested, and we will tape out all the data which is causing the impulse. So um, let's say we want something like this. So over here it goes from 0, it waits for the data, and again it goes to 0 in the ends. So in the ends of the period, it is at 0. So this is something called as Hann-Window, and this is nothing but it seems like a cos signal which is uplifted by half. So it is given by 0.5 1 minus cos n by record length times 2 pi, where n lies between 0 to n minus 1, because we are in that's what our samples are, right? That's our period is from 0 to n minus 1. So let's see what a Hun window does to our sinusoid, which lies onto a bin. So let's first take a case where the condition Fin by Fs is satisfied, and the sinusoidal or f, like basically Fin, lies onto a bin. So let's see what our Hun windows does to our output spectrum. So let's say we have a input which is cos of a of n. So this is a sinusoidal input, and instead of taking a rectangular window of m samples here, now we will take a Hann window. So this is a signal whose discrete Fourier transform is being sampled when we compute the discrete Fourier series, as we said over here. So basically, we multiply. Yeah, so we window the sequence before taking its Fourier coefficient. So that's what we mean. So this is the signal, and this is a signal whose DFT has been sampled before we compute the Fourier series. So as we are considering only n bins lying from 0 to n minus 1, we can think of above signal, this whole signal, as if being multiplied by a rectangular window of size n. So it is the same thing. We can realize it with the same. What happens with this signal is basically this cos of an is getting multiplied by half. So it's half of cos of an minus, it's also getting multiplied by half of cos of 2 pi by n times n. So basically, this gives us a magnitude of half, or this contributes to a half magnitude of original signal. And this is something like cos A, cos B. So which gives us which gives us two contributions. One is 1 by 4 cos A plus 2 pi by n times n, and one is 1 by 4 times cos A minus 2 pi by n times n. So basically, if this A lies on a bin, then A plus 2 pi by n and A minus 2 pi by n will also lie on a bin, and all other bins are 0. Hence, for a Hann window, we expect 3 peaks basically at A, the other one to the left of A at a minus 2 pi by n, and the other one at right of the a, which is a plus 2 pi by n. So we expect three peaks in the plot of coefficients of the discrete Fourier series, and also the magnitude of peak of the coefficient of a is contributing half of the input signal, and other two peaks which are resembling a plus 2 pi by n and a minus 2 pi by n will give an amplitude contribution of 1/4 of the input. So we can analyze this using a Python plot. So as mentioned on the screen, so there initially we had this plot, right? So this is the plot for rectangular window where we had two bins. So now this is the plot if we zoom it properly. So we have one bin which is a minus 2 pi by n, other bin a plus 2 pi by n, and at a itself we have a peak. So we have three peaks, and when we resemble it or when we compare it with our uh, rectangular window, so if rectangular window had a magnitude of this thing, so this is in dB, right? So now the as we discussed over here, if the screen is visible, the main, this contributes to,
Yes, it is visible.
yeah. So this contributes to half of the main signal, right? So basically when we talk about half, so it is reduced by 3 dB. So we can see over here, this is the minus 3 dB, and for other two it is minus 6 dB. So now I'll provide you this code, Python code. So again, play with the values, and uh, I want you guys to play with the values and understand how the comparison is being held on with the Hann window signal and rectangular window signal. So play with the values, play around the code, and in the next video, we will discuss more when the ratio is not satisfying for the bins to be accurate. So that's all for this video from my side. Thank you so much. So if you have any doubts, let me know.